Well, hello and welcome to another one of my videos. Now, you know, I quite enjoy topics that are sort of a little bit off the beaten track and quite interesting. They don't change the world or anything like that, I don't think, but they're interesting all the same. Now, you know that probably that I've been interested in energy and electricity generation and stuff like that, and atomic things like how stuff holds together, how the atoms work and all that sort of thing. And one of the molecules that I've been particularly interested in recently has been that of water. A lot of people are interested in water not only because it keeps us alive and that we should keep it clean and it's a resource that we need to look after and all that. It's also being investigated for its energy potential, not only hydroelectrical generation potential, but for the actual molecule itself, by splitting the oxygen and the hydrogen atoms from the molecule to then use the hydrogen as a fuel. Plants already have figured this one out millennium ago and have managed to harness the sun's energy to split the water molecule in photosynthesis to then use that process to process energy and all of their functional needs, which we in turn rely on to stay alive. Well, water, we have found out or know, can exist in 3 different states. It's a very interesting molecule that way. It can be a gas, or it can be a liquid, or it can be a solid. The solid being ice, of course, if it gets cold enough. And that's very interesting. Not many other molecules can do that sort of thing with such ease. And it's very important for us that it can do that. Now, recently I came across information that indicated that there is actually a 4th state that water can have, somewhere between solid and liquid, and that is being liquid crystal. Now, that is very interesting because that state of being a liquid crystal has electrical properties to it, and it has potential for some very important things, really, and even the functioning of our body is reliant on it. And I found out a few things that I never knew before. I'll explain how it works and tell you about those other things as well. Now, in their basic state, the water molecule is an oxygen and 2 hydrogens. Now, because the hydrogens only have 1 proton, 1 neutron, 1 electron, but the oxygen has 6 or 8, it has a lot more, it means that there's a lot more attraction in the oxygen than there is in the hydrogens. So that when you get a number of the oxygens and hydrogens together, they will attract to each other and start to group together, and then you're going to get the liquid state. It gets to the point where they start to get to the point where the oxygen and hydrogens can start to attract together and sort of make a sort of a bond there, and then the next one can go like that, and then it can then make a connection, and just the attractions of the oxygens with another water molecule's hydrogen can then start to form a little bit of a network. Now, when they get cold, you generally get 6 of them together, and they form a hexagonal pattern like that, all attracting to each other, and then they start to, they're only one atom thick, and then they stack one on top of the other, so that an oxygen attracts another oxygen, and they line up like a stack of plates, and that's what gives us the solid state of the water. But what happens before that is instead of the oxygens lining up above oxygens, if it shifts by 60 degrees, I think, the oxygen can line up over the top of a hydrogen, say it like that, over the hydrogens, and then you get them staggered so that they line up, stack in plates, and there is a pull between the oxygens and the hydrogens, oxygen hydrogens, above each other, stacked like plates, so that you get the thing holding together in a structure, a crystalline structure. But because they're not actually bonding together like the solid plates of ice, they move. There's a certain amount of movement, so it's liquid enough to move, but it's structured enough to be crystalline, and that's how you get your crystalline structure. So you can see here that the oxygens are all lining up one on top of the other, and the positives between them are on top of each other, and that's your ice solid state. But when you turn every second one so that you've got two oxygens and a hydrogen, and the hydrogen is over the oxygen in between the other two oxygens, and the next one is staggered, so you've got right down the center here on each of the 6 faces, you've got a positive, negative, positive, negative, positive, and it's alternated with sufficient attraction to hold the structure, but not sufficient to hold it rigidly. So it's a liquid liquid crystal structure. Now, when you have a surface like here, that it's a solid surface, and it will has a polarity that will allow the water molecules to stick to it, like this. That's an aqueous, it's very water friendly, it'll stick. Now, because of that proximity, you're going to start getting layering of these water molecules in that liquid crystal layering system, and so that you get within, say, 100 nanometers of a surface here, you get a layer of liquid crystal, and then they get less and less as the energy dissipates until you get out into just your normal water molecules out here. Now, that layer can become quite precise, of 50 to 100 nanometers, and the combined electrical sum of the charge on that water becomes such that it is the opposite polarity to the sum charge of the water out here. So the water out here has a charge, and at the surface it has another charge. So if you were to take a probe and put it into this layer here, and a probe into here, the disparity or difference between the charge of this water and that water means that you can get a current. If you join the wire, for example, here, joined it, the 2 points, you will get a flow of electrons of charge going from one water state to the crystalline water state, or vice versa, I can't remember which, so you can get an electrical flow. Now, that has potential for generating electricity on a nanometer scale. An application that happens in our body is that you get a capillary. If this is a tube, a capillary that blood is going to go through, like red and white nebulae cells, every surface of the capillaries then builds up a layer of crystalline water, and that, wrapping around the whole cylinder, sets up a magnetic field through that electrical disparity or unevenness, and then it creates a sort of a magnetic force field in the middle that makes the cells stay in the middle of the capillary, and not only that, it makes them move along the capillary. So therefore, the blood that is going through our capillaries is not actually moved by the pumping of our heart, because the capillaries are so small and the pressure needed is so high. We always thought that our blood was moved through the capillaries by our heart. But when it gets to a capillary level, it's actually the water coating the inside of the capillary, setting up a magnetic field, an electromagnetic field that makes the blood flow through. Now they have found that it is that the increase or the build-up of that water level on the surface is increased quite dramatically by infrared wavelengths of energy. So the energy for those to stick together and build up that crystal, water crystal level, or liquid crystal layer to set up the magnetic field actually comes from the ambience. It doesn't come from our own energy source like the food we eat. Part of the circulation of our blood is moved through our capillaries by ambient energy setting up this magnetic field in our capillaries. That is really amazing, the fourth state of water with these electrical properties, and we've only just begun to consider the ramifications of this and the potential of this phenomenon. So that is actually quite exciting, to think that part of the energy we use to stay alive is not the food we eat, and then it begs the question of how much of the energy we need actually comes from our food and how much doesn't actually come from our food but from the air around us, and how much of that air around us we will be able to capture for useful application when it comes to crystalline water in that situation. Got some exciting things to think about.